Okay, this video is review for your bonding quiz and also the practice quiz that we're doing in class on Monday, the key for that. You need to make sure you understand each concept in this video, and you also need to understand how to do all of the problems on the practice quiz. The practice quiz is very similar to the real quiz that you will have in class on Tuesday. Additionally, your KIA 8.2 quiz is due Monday night, and it has similar questions as well. The key is all multiple choice. Your quiz on Tuesday will not be multiple choice. Okay, so the first thing, you need to be able to draw Lewis structures for molecules and polyatomic ions. Now, when I say Lewis structures, that means with single, double, and triple bonds. Lewis structures are meant for covalent bonds or bonds between two nonmetal atoms. Okay, so that's when you know how to draw a Lewis structure. Okay, so to draw a Lewis structure, the first thing you need to do is you need to count the number of valence electrons that you have. So for O3, which happens to be a molecule of ozone, oxygen, based on its position in the periodic table, has 6 valence electrons, and there are 3 oxygen atoms in O3. So I'm going to do 6 times 3, which is 18 valence electrons. And it's difficult to count, or it's tedious to count 18 valence electrons, so it's easier if you will count pairs of electrons. So if you take the total number of electrons that you have, divide by 2, that'll give you your pairs. So I have 18 total valence electrons, or 9 pairs of electrons that I need to represent. After you count your pairs, write down all of the atoms in the molecule and single bond all of them. Single bond all of them. Then satisfy the octet. That means give every atom in your molecule 8 valence electrons. Last step, count your pairs. If you are over your pair count, meaning if I'm supposed to have 9 pairs of electrons, but my structure has 10, then I need to get rid of a pair and either double or triple bond some atoms within the molecule. Okay, so here's how we're going to do that. I'm going to draw my 3 oxygen atoms. I'm going to single bond. Okay, and I'm going to satisfy the octet. So right now the middle oxygen has, each of these single lines represents 2 electrons, or 1 pair of electrons. So right now this oxygen atom in the middle has 1, 2, 3, 4 valence electrons. So if I do 5, 6, 7, 8, it has an octet. Okay, and I'll continue to do that octet around the other oxygen. So now this oxygen on the right end has 1, 2, 3, 4, 5, 6, 7, 8. I'm going to do the same thing to the oxygen on the left. Okay, so now every oxygen in the molecule has an octet. Now I'm going to count pairs. So right now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 10 pairs of electrons. I can only have 9 pairs, but each oxygen in the molecule must still have 8 valence electrons. So when I'm over my pair count, then I need to double or triple bond some of the atoms in the molecule. So what I'm going to do, so I can put a triple bond, I can put a double bond right here. And if I put that double bond there, I need to get rid of some pairs of electrons so that I have still an octet of 8 valence electrons around each oxygen. So once I make that double bond, like I said, I need to get rid of some of these electrons. So I'm going to get rid of this pair right there. And then now this oxygen has 1, 2, 3, 4 pairs, or 1, 2, 3, 4, 5, 6, 7, 8. It's fine. The oxygen in the middle, though, has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's got 10 valence electrons. It can only have 8. So I'm going to get rid of another pair. And right there, that will satisfy the number of pairs that I need and also my octet. So let's double check. So I'm going to do my pair count first. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 pairs. Got it. I'm going to check now my octets. So I have 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. This atom on the left is fine. Central atom. 1, 2, 3, 4, 5, 6, 7, 8. Central atom is fine. Oxygen on the right. 1, 2, 3, 4, 5, 6, 7, 8. This oxygen on the left, or I'm sorry, on the right is also fine. So not only have I met my pair count, but I've also satisfied the octet. And those are the two things you must do in any Lewis structure that you draw. Now, you could have drawn your Lewis structure the same way, except you could have put your double bond on the right side of the molecule as opposed to the left side. And we'll talk about what that is in just a minute. But right now, I just want to make sure, can you draw a correct Lewis structure, satisfying the octets of all the atoms that need to have an octet? And can you meet the pair count of valence electrons that must be in your Lewis structure? All right, second thing you need to do is draw the Lewis structure for the nitrite ion. And nitrite is NO2 with a -1 charge. Okay, it's the same thing. Start counting up the valence electrons that you have in the atoms in your particle. So this is a polyatomic ion. It's got covalent bonds between the atoms, nitrogen and oxygen, because you have non-metals only. But because it has this -1 charge, it acts like an ion. So a polyatomic ion is a group of non-metal atoms that are covalently bonded. They're sharing electrons, but they have a charge, either a negative charge for most of our polyatomic ions or a positive charge. Okay, so nitrogen has 5 valence electrons. From the periodic table, you can look and see it's in group 15, so 5 valence electrons, and only have 1 nitrogen in the polyatomic ion. Okay, oxygen has 6 valence electrons. From its position on the periodic table, it's in group 16, so 6 valence electrons. And there are 2 oxygen atoms in this polyatomic ion, so 6 times 2. The -1 charge, -1, you got to say this to yourself, negative means that you gain. Negative means that you gain. So -1 charge means that I have 1 more electron that I'm gaining, okay? So +1 here. So if you add up 5 plus 12 plus 1, that's going to give you 18 valence electrons, and 18 valence electrons equals 9 pairs of valence electrons, okay? So same procedure as the one before. Single bond all your atoms, satisfy the octet rule, count your pairs. If you're over the pair count, then double or triple bond is needed, okay? So by the HONC rule, the H-O-N-C, our nitrogen is going to go in the middle. Okay, oxygen is going to go on either side, so I'm going to single bond those because that's what I need to start out with. Satisfy the octet rule, so I'm going to put 2 more valence electrons here and 2 more here. So now nitrogen has an octet, and then each of the oxygens will need 3 lone pairs or unshared pairs around them. And if you were paying attention on the O3, you're going to see that the nitrate, the NO2 minus, is very similar to that. Okay, so now each atom has 8 valence electrons around it. But if I do my pair count, so I have 1, 2, 3, 4 pairs, 5, 6, 7, 8, 9, 10. I'm 10 pairs, and I can only have 9. Each atom still has to have an octet, so I can't just get rid of a pair and say, I'm 9 pairs. I've got to do something else. So if I'm over my pair count, then double or triple bond. Okay, so let me get my eraser. So I can either double bond on the left or I can double bond on the right. This time I'm going to do it on the right. Okay, so I double bonded there. So when I made that double bond, now I'm going to have to get rid of a pair or 2 pairs of valence electrons. Okay, so I'm going to take a pair off of this nitrogen, and the reason I'm doing that is because if you look right now, the oxygen on the left end is fine. It has 8 valence electrons. 2, 4, 6, 8. The nitrogen, on the other hand, has 2, 4, 6, 8, 10. Can't have more than 8. So I'm going to take off a pair there. And now nitrogen has 8 valence electrons. It's fine. Over here on the right, though, this oxygen has 2, 4, 6, 8, 10. Can't have that. So I'm going to take off a pair here. And it doesn't matter on the oxygen or on the nitrogen which pair you take off. You just need to remove a pair. Okay. So now this oxygen has 2, 4, 6, 8 pairs. So it's fine. And then let's do our overall pair count. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's how many pairs I needed. I needed 9 pairs. So this is correct. The only other thing that I need to do is put this ion, because it's an ion, it's got a negative charge. I need to put it in brackets to signify that it's an ion, and I need to put the charge on the outside of that. So let me do that. All right, so there I have my nitrite ion correctly drawn with a -1 charge. And again, this double bond could have gone over here with this oxygen, and I would have removed a lone pair of electrons over here instead. So I've got here the actual, not my scrawl with on my mouse pad, but I've got the actual Lewis structures for O3. So you can draw it like this. You can also show, if you've been in class and know that the shape of the molecule, we're going to start looking at the shapes of molecules and polyatomic ions. You can also draw it like this, so it's bent. The main thing with Lewis structures, you're looking for the right number of valence electron pairs, and then the octet rule around the atoms that need the octet. And that would be everything except for hydrogen and boron. Okay, every other atom needs an octet. So you can draw it like that. And then down here, move this out of the way. Here's your nitrite ion. And nitrite can either be represented like this, with the double bond on the right, or with the double bond on the left. So what I've been kind of dancing around but have not really talked about is the idea of resonance. So sometimes there are molecules and polyatomic ions whose structure is not adequately described by just one Lewis structure. So ozone, we drew, can have the double bond either on the left or on the right or the left. So we expect the double bonds are shorter and stronger than single bonds. So we expect the double bond to be shorter than the single bond. So where should the double bond go? Equivalent Lewis structures are called resonance structures. So the real Lewis structure for O3 is actually sort of a hybrid between these two. We're not going to focus on that too much. All I need you to know for right now is that resonance means that this double bond, which is really not quite a double bond, it's sort of a hybrid bond. But when you draw your Lewis structure, you can either draw it on the right side of the molecule or on the left side of the molecule. Resonance means that the double bond, or if it's a triple bond, but for most of ours it's going to be a double, that the double bond is not locked in a particular position. Okay, so it can be represented in more than one position. So there's resonance for our for our O3 for ozone. So you can think of resonance kind of like paint. When you go to the store and you ask for green paint to be made, green paint is made of both blue and yellow paint. So if you ask for green paint, you expect the paint to stay green. You don't expect for it to flip between yellow and blue, yellow and blue. You expect for it to stay green. Same thing with resonance. So this double bond here is not really flipping or changing positions. Instead, you've got almost like a hybrid bond. So the hybrid is represented by dots. Then you wouldn't have this here. But you would have a hybrid bond that would act between all three of those oxygen atoms in the molecule. With resonance, the electrons are not locked into place, so the arrangement of electrons is a blend of each of the resonance structures. All you need to know for my class is that if you have a polyatomic ion or a molecule that can show resonance, you need to show all of the resonance structures that are available to that particle, to that polyatomic ion or molecule. So for a check for understanding, here you go. Draw all possible resonance structures for the nitrate ion. So if you need to pause me right now, and then I will show you on the next slide all three resonance structures for NO3 minus 1. Okay, so I've done here what I've told you to do on the previous slide. So when you're trying to draw a Lewis structure, again, count your valence electrons, add them up, find the total number, divide by 2 to find the pair count. How many pairs of valence electrons do you need? Then single bond all of your atoms, satisfy the octet rule, count the pairs of valence electrons. If you are over your pair count, then double or triple bond. Okay? So with NO3 minus 1, I have one nitrogen atom, and nitrogen has 5 valence electrons, so 5 times 1. For oxygen, I have 3 oxygen atoms. Each oxygen atom has 6 valence electrons. So 6 times 3 is equal to 18. And that -1 charge right there means that 1 valence electron was gained. Negative means that you gain, okay? So I have 15 plus 18 is 23, plus 1 more is 24. So I have 24 valence electrons I need to show in my Lewis structure. So to make that easier, 24 divided by 2 is 12 pairs. So I need to show 12 pairs. So put by the honk rule, and that's HONC. Okay, and so the way that works is as you go to the right, those are the atoms that will go more to the middle of the molecule or the polyatomic ion. So nitrogen should go in the middle. Oxygen should go on the periphery of the polyatomic ion. So I have nitrogen and then 3 oxygens, and I single bond everything. Okay, did that. Then satisfy the octet rule. So this nitrogen now, if I put a lone pair up here, has 1, 2, 3, 4, 5, 6, 7, 8. It's good. Each oxygen has 1, 2, 3, 4, 5, 6, 7, 8. So all of your oxygens are good. Then count the pairs. All right, so I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I am over my pair count. I can only have 12 pairs, and I have 13. So at this point, I need to get rid of one of my valence electron pairs. The only way to do that and to keep the octet on all 3 atoms is if I double or triple bond. Okay, so I'm going to double bond. I'm going to put my double bond right here. And then I'm going to squiggle out these electrons so they're no longer there. And I'm going to squiggle out those. Okay, let me erase those. Okay, so let's see. So I've actually erased those pairs instead of just squiggling them out. So then now let me count. So around nitrogen I have 2, 4, 6, 8 electrons. It's fine. The oxygen over here has 2, 4, 6, 8. Good. 2, 4, 6, 8. Good. 2, 4, 6, 8. Good. My octets are fine now that I've made this switch with adding a double bond and taking away 2 pairs. Then let me do my pair count. I need 12. I was at 13. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Perfect. I have my Lewis structure. Okay, and you could have put your double bond in this location on the left, down here, or the location on the right. So that's an example of resonance. So where it says draw all possible resonance structures, this is what you should have drawn. Okay, so because that double sort of hybrid bond can be over 3 different locations, you need 3 different resonance structures. The number of resonance structures depends on the number of locations where you can locate the double or the triple bond, okay? And it has to be between the same 2 types of atoms. So because these bonds between nitrogen and oxygen are identical bonds, resonance can exist in 1, 2, or 3 places. Okay, so I should have 3 different structures to show that. And nitrate is a polyatomic ion. It's got a charge, so I need to put it in a bracket and put the -1 charge. So you'll have one like this tomorrow on your quiz, and or Tuesday on your quiz, and there's one like this on the practice quiz that you're doing in class on Monday. All right, so we need to talk a little bit about some terms that you probably use frequently, but maybe haven't thought about exactly what they mean. So, let's see. Okay, so a molecule refers to a group of covalently bonded atoms. That means you're looking for groups of non-metal atoms that are bonded. That's a molecule. Okay, and a molecule is the simplest unit of a covalent compound. Remember that hydrogen is a non-metal, even though it's with group 1. So if you see hydrogen within a formula, please don't mistake it for a metal. Okay, it's definitely a non-metal. A formula unit is the simplest unit of an ionic compound. So you're going to look for a metal and a non-metal. So your classic example, NaCl, one of those is a formula unit. Okay, formula unit is looking at bonds or attractions between metal ions and non-metal ions. An ion is a charged particle. So you could have like aluminum with a +3 charge, and that's an ion. Or you could have sulfur with a -2 charge, and that is an ion. Polyatomic ions are charged particles, but they're charged particles of covalently bonded atoms. Okay, so the one we just did, NO3 with a -1 charge, it's an ion because it's got a charge, but it's a polyatomic ion. Polyatom just means many atoms. Okay, so a polyatomic ion, look for more than 1 atom in the ion and look for a charge. If you have compounds that are ionic, but they contain polyatomic ions, so like potassium nitrate, calcium carbonate, strontium nitrate, magnesium phosphate. Ionic compounds that contain a polyatomic ion have both ionic and covalent bonds. The covalent part comes from the non-metal atom covalent bonding in the polyatomic ion. The ionic part comes from the attraction. Excuse me one second. Okay, sorry about that. Just remember, if you have a compound that contains a polyatomic ion, it has both ionic bonds, and that's the attraction between, so like in potassium nitrate, your potassium ion has a +1 charge. So the ionic part is the attraction between the ions, +1, -1 attract. And the covalent part, the covalent bonds in there, come from the polyatomic ion, the non-metal atoms bonding in that. Okay, so let's do a little bit of practice and make sure you kind of understand what's going on. Okay, so what is it? So your choices are molecule, ion, formula unit, or atom. So let me kind of scooch some of this around. So CO2, non-metal, 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 non-metal. Okay, that's a molecule. So CO2 is a molecule. Right, next, NO2 -1. This -1 right there tells me that I have a charge. Charged particles are called ions. This is a special kind of ion. This is a polyatomic ion because it has more than one atom in the ion. Okay, remember polyatomic ions, covalently bonded groups of atoms, and they have a charge. MgCl2. Well, Mg is a metal. Cl, non-metal, so MgCl2, metal, non-metal, metal, non-metal. That is a formula unit, okay? So, look there and we're good. O2. I have two atoms, so I'm not just an atom. My two atoms are identical, and we've talked about this a lot. So, my two atoms are identical, so I have a molecule. It's a special kind of molecule. It's a diatomic molecule, okay? Non-metal atoms bonded together, it happens to be the same two atoms there, so it's a diatomic molecule. Ag, silver. It's not a molecule, I've got a metal, so that's out. It's not an ion, it doesn't have a charge. Formula unit means metal, non-metal. Nope. Atom, it's just an atom. Okay, I just have an atom there. There's just one single thing there. It happens to be a metal atom, but it's an atom. Ag+1. Okay, now I have silver, but I have a +1 charge. So right there, boom, it's an ion. An ion is a charged particle, so this happens to be a silver ion. PO4 -3. Again, a charged particle, so it has to be an ion. Okay, this happens to be a polyatomic ion because it has more than one atom there. Mg3 PO4 2. That's a big formula. Okay, it's not a molecule because I've got magnesium, a metal in there. Molecules are non-metals only. It's not an ion, there's no charge. It's certainly more than an atom. This is a formula unit. It's the simplest part of an ionic compound. Okay, and because this formula unit has both, or has a polyatomic in it, it actually has ionic bonds and covalent bonds. But the whole structure here is called a formula unit, the simplest part of an ionic compound. PCl3, not an atom, it's got more than one thing. Not an ion, no charge there, so it cannot be an ion, so it's either a molecule or formula unit. Phosphorus and chlorine are both non-metals. Non-metals are molecules, so this is a molecule. Cl2, a lot like O2. It's going to be a molecule. It's going to be a diatomic molecule. So just a reminder here, ions have a charge on them. They're a charged atom or a group of atoms, and the charge is caused by either a loss or gain of electrons. Okay, so this would be I lost an electron, the negative charges would be I gained an electron. Formula unit is the simplest unit of an ionic compound. In order to be a formula unit, you must have both a metal and a non-metal, or a metal and a polyatomic ion in your formula. Okay, molecule. Molecules are the simplest unit of a covalent compound and contains only non-metals. So here are your examples. And remember that hydrogen, even though it's with the group 1 metals, is not a metal. So don't mistake that. And then if you just have one type of element in the molecule, as long as there are more, 2 or more atoms there, it's still a molecule. So N2 is a diatomic molecule. Okay, let me pause there. Okay, so now we're going to get into what we did in class on Thursday. And if you were not there on Thursday, you'll want to pay attention to this. So VSEPR theory, VSEPR stands for valence shell electron pair repulsion theory. So that means that valence electrons, both lone pairs and shared pairs, repel each other. They try to push away from each other as much as possible. So your Lewis dot structures, or your Lewis structures, to show molecules and polyatomic ions, are good representations of how molecules and polyatomic ions are put together, but they don't really show the three-dimensional geometry or the shape of your structure. So the VSEPR theory is a way to show how your Lewis structure has a shape. VSEPR theory states that electron pairs repel each other as much as possible so that the molecules or the polyatomic ions are going to acquire shapes to make sure that these pairs are as far apart as possible. So you've got to think in 3 dimensions. So in class on Thursday, you got an orange sheet. Let me make this bigger. There we go. You got an orange sheet that looked like this. Now, the bond angles and hybridization you don't need to know or memorize. It may be helpful for you to think about bond angles, but I'm not going to ask you any questions on that. There are 5 shapes that you need to memorize. You need to be able to go from the Lewis structure to the shape and then tell me what the molecular shape is. So the first example I have here is of a linear structure. So linear just means it looks like a line. The way you're going to tell if you have a linear structure or not is the number of atoms that are bonded to the central or the middle atom. So in carbon dioxide, carbon is your central atom. If there are either 1 or 2 atoms bonded to the central atom and no lone pairs of electrons on the central atom, it's a linear structure. So if I have 1 or 2 atoms bonded to the middle atom and no lone pairs on that central atom, it's linear. Then, like water, is similar, but the problem is it's got lone pairs of electrons in the central atom. So here's how this works. So water, H2O, oxygen's in the middle. You have 2 atoms bonded to the central atom, but there are also 2 lone pairs of electrons on that central atom. So those 2 lone pairs take up some space, and so they cause, my lone pairs are up here, so they cause repulsion, and they push away from each other, so it causes your bonded pairs of electrons to have to get closer as well, okay? So that's a bent structure. Now, next 2. If I have 3 atoms bonded to the central atom, I can either have a trigonal planar structure or a trigonal pyramidal or pyramidal, however you want to say it, structure. So in BCl3, I have 3 bonds, 1, 2, 3. So 3 atoms bonded to the central atom, but there are no lone pairs of electrons. So those 3 bonds can be as far apart as they can get, and as far apart as they can get is 120 degrees. Okay, so I've got a circle divided into 3 parts, 120 degrees. Trigonal pyramidal or pyramidal, still 3 atoms bonded to the central, so nitrogen's in the middle, 1, 2, 3 atoms bonded to the central. But nitrogen has this lone pair of electrons on it right here, and that lone pair, represented over here, will push away, and it'll take up some space. So instead of being able to be 120 degrees apart, that lone pair of electrons will repel the bonded pairs. And now I have, instead of a planar structure, I have a pyramidal or pyramidal structure. So when I have 3 bonded atoms, but 1 lone pair of electrons on the central atom, then I'm going to be a pyramidal structure. And then the last shape you'll need to know is tetrahedral. Tetra means 4. So if I have 4 atoms bonded to the central atom and no lone pairs on the central atom, I'm a tetrahedral structure. It looks like this. Okay, so you'll want to take some time looking at this. And you have a lab that we did in class where y'all drew the Lewis structures and then built the molecules with the ball and stick models. And we also, y'all did on Friday, a review with this. So you'll want to take some time and look back over this in addition to the practice quiz that we're getting ready to go over. Okay, so now we're going to look at, do you understand how you can go from Lewis structure to the shape, to the molecular geometry of your molecule. I'll make a separate video for the practice quiz that we're doing. You'll want to watch both, okay? So what's the molecular geometry of these particles based on VSEPR theory? So the first two structures are the same. It does not matter how you draw the Lewis structure in terms of are you showing the shape or not, okay? If I look at both of these, the one on the right gives you a little bit more idea of the shape, but you could draw the one on the left and be just fine and get that correct, okay? So the shape of this Lewis structure, so I have a central atom, I have 1, 2, 3 bonded atoms, and no lone pairs of electrons on the central atom. So 3 bonded atoms, no lone pairs. So this is going to be a planar structure. So CH2O is a trigonal planar geometry. If I look at NH3, I have 3 bonded atoms, but now this lone pair right here is sneaky. That lone pair pushes on all of my shared pairs. So NH3 is not going to be planar. My other choice for 3 bonded atoms is trigonal pyramidal. And since I have that lone pair of electrons, this structure is trigonal pyramidal. Okay? Do you see the difference? These two structures and this one have 3 bonded atoms, but there are no lone electrons on the central atom in CH2O, and there is a lone pair of electrons on the central atom in NH3. Okay? So planar, pyramidal. Next, I have CH3Cl. So you can draw it like this, or you can draw it like this. And this chlorine can be in any of these positions. It doesn't matter. So I have 1, 2, 3, 4 bonded atoms in each of these, and no lone pairs of electrons on the central. So it's a tetrahedral shape. So these are tetrahedral. All right, with the water. Water can be drawn like the top structure or like the bottom structure. Either one is equally correct. You need to be careful though, because if you just draw this, you say, oh, it's a line, it's linear. It's not linear. The reason why it's not linear cannot have any lone pairs of electrons on the central atom. Linear is a central atom with either 1 or 2 bonded atoms and no lone pairs on the central atom. Well, you've got 2 lone pairs on that central oxygen, so it cannot be a linear structure. This is going to be bent, okay? Bent has 2 bonded atoms and either 1 or 2 lone pairs of electrons on the central atom, and I got that on my water. Okay, so this is bent. On the other hand, carbon dioxide down here, I have 2 atoms bonded to the central atom, but carbon doesn't have any lone electron pairs on it. So CO2 is going to be a linear molecule. BF3, 1, 2, 3 bonded atoms. No lone pairs on the central, so this is trigonal planar. And then HF, I just have 2 atoms there. I don't really have a central atom. When that happens, this is going to be a linear structure. Okay? And so I'm going to end this recording right here, and I'll do a second recording. Hopefully it won't be quite as long for the practice quiz for bonding. Okay?